Assalamu alaikum everyone. So we were studying about the chapter number 6, which was about the understanding about process conditions, in which we mainly talked about the temperature and the pressure conditions. And we have seen that there is some allowable conditions that can be easily achievable in terms of temperature and pressure. For example, the temperature range from 40 to 260 degrees centigrade. We can achieve this temperature very easily using some kinds of simple heating streams or by burning some of the fuel quickly. And in terms of the pressure conditions, ranges from 1 to 10 bar that can be easily achieved by using some kind of compressors or the pumps, depending on the material that we are using. Either it can be a gas or a liquid. Okay, so now we talked about the temperature and the condition, and we saw that if we are going above 10 bar pressure, for example, then what we have to do, what kind of equipment we can use, and how it can impact the cost of the equipment. And then we actually talked about also, if we go below 1 bar pressure, then the size of the equipment would be increased due to the expansion of the process streams. And in the same way, we talked about the temperature range. If you want to go beyond 260 degrees centigrade, then you have to use some kind of special heaters. And if we are going below 40 degrees centigrade, then we have to use some kind of refrigeration process in our process. And then we talked about the impact of high temperature on the material strength, and we saw that the material strength would be significantly decreased if we go beyond 350 degrees centigrade. And we try to solve some of the examples to see the material strength effect due to the increase in the temperature. Now today we will see some of the more conditions if we want to go beyond this acceptable temperature and the pressure range, and we will see that what could be the justifications and when we can actually cross those boundaries. Now let us see this one. Table 6.1, possible reasons for operating reactors and separators outside the temperature ranges of the special concern. So we will see some of the conditions here, and we will see that what could be the justifications when we can go beyond this temperature. For example, if we are dealing with some kind of a process stream that is above 2 degrees, 250 degrees centigrade, then what could be the justifications? In terms of reactors, maybe we can go beyond this temperature to if favorable equilibrium conversion for endothermic reactions are required. So for the endothermic reactions, we can go beyond this temperature range. If we want to further increase the reaction rates, we can go beyond 250 degrees centigrade. Similarly, if we are going beyond 250 degrees centigrade, one of our aim would be to keep the reactants and products into the gaseous phase. So it can be one of the reasons. And obviously, if the selectivity of the product can be improved by going beyond 250 degrees centigrade, then we can use the higher temperature. Now, what could be the penalties for operating at this condition? So if we are going beyond 250 degrees centigrade, then what could be the penalties on the process? Then we have to use special process heaters. We have to use some kind of special process heaters to achieve that high temperature. If the temperature is above 400 degrees centigrade, requires special materials of construction. So we have solved some examples, and we see that how the material strength is highly affected by the increase in temperature. Okay, so we have to consider some special materials of construction if we are operating our process above 400 degrees centigrade. Now, in terms of separators, obtain a gas phase required for vapor liquid equilibrium. So if you want to have a gas phase in the separation, then we can go beyond 250 degrees centigrade. Now let us see if we want to operate our process below 40 degrees centigrade. That is also the that doesn't lie within the boundary of the temperature. So if we are operating the process below 40 degrees centigrade, then what could be the reasons? Favorable equilibrium conversion for exothermic reactions. So if we are having some kind of exothermic reactions, and to if you want to achieve the equilibrium, then we can operate the process below 40 degrees centigrade. Temperature sensitive materials, so if we are dealing with some kinds of products that are temperature sensitive, then we can go below 40 degrees centigrade. Obviously, if you want to improve the selectivity of our product, and if you want to maintain a liquid phase, so at this low temperature, below 40 degrees centigrade, most of the liquids they remain as in the liquid phase, so it can be one of the reasons. Now, what could be the energy penalties? So, to go below 40 degrees centigrade, we have to use some kind of expensive refrigerant, and then we have to use some kind of additional refrigeration cycle, may require special material of construction for very low temperature, and obviously for the high temperature above 260 degrees centigrade, and also if you are dealing with those streams that are below 40 degrees centigrade, or they have some cryogenic conditions, then we have to also consider the special material of construction. Now, in terms of separators, if we want to operate the separators below 40 degrees centigrade, then what could be the aims? Obtain a liquid phase required for vapor liquid or liquid liquid equilibrium. So, if we want to keep the liquid phase within our process, or we want to have an equilibrium between the vapor liquid or the liquid liquid, then we can go below 40 degrees centigrade. Obtain a solid phase for crystallization. So, if we are carrying out the crystallization process in the separator and we want to get the solid phase, then we can go less than 40 degrees centigrade. And temperature sensitive material, so it is similar for the reactor and the separator. So if you are dealing with some kind of some temperature sensitive materials, we can operate the process below 40 degrees centigrade. Now let us see some of the more reasons, possible reasons for operating reactors and separators outside the pressure range of the special concern. Now we saw that the pressure range from 1 to 10 bar, it is a normal pressure range, and if you want to go beyond 10 bar or below 1 bar, then we have to see, and we have to justify the reasons of operating the process beyond those limits. Okay, now in terms of reactors, we can go beyond 10 bar pressure if we want to have favorable equilibrium conversion. So to get the equilibrium quickly, we can go beyond 10 bar pressure. Increase reaction rates for the gaseous reaction due to higher concentration. If we want to increase the rate of reactions, then we can go beyond 10 bar. And if we want to maintain the liquid phase within the reactors, then we can operate the reactors beyond 10 bar. Now, what could be the energy or the penalties on the process or this operation? It requires thicker walled equipment. If we want to go beyond 10 bar, then we need to have the equipments with the thicker wall to just withstand that high pressure. Requires expensive compressors if gas streams must be compressed. Okay, so if you want to go beyond 10 bar, then we have to use some kind of expensive compressors for the compression of the gases, or in case of liquids, we have to use the pumps to achieve that high pressure. Now in separators, obtain a liquid phase for vapor liquid or liquid liquid equilibrium. Now if you want to go beyond 10 bar, one of the reason it could be to have the liquid phase for vapor liquid and liquid liquid equilibrium in the separators. Okay, so you know that when you increase the pressure, we can convert the gases more into the liquid, and so we can have more liquid phase when we increase the pressure. Now, if we want to operate the reactors or the separator below 1 bar, then what could be the justifications? The first one, the favorable equilibrium conversion. So, in most of the reactors, what could be the reason going beyond the allowable temperature and the pressure range? It could be the favorable equilibrium conversion. So, you would see this comment in all of these, all of those conditions. Then the second thing, maintain a gas phase. So if you are operating any process below 1 bar, then one of the reason could be to have the gas phase of the reactants and the products. Now, what could be the penalties on the process? Requires larger equipment. So we discussed this thing. If you are going below 1 bar pressure, then the size of the equipment would be increased. Special design for vacuum operation, and then going below 1 bar, you need to have some kind of operate vacuum system in the process, and how you can actually air leaks into equipment that may be dangerous. And we have to also consider the air leaks because our ambient pressure is at 1 bar. So if you are operating any process below 1 bar, so any kind of leakage would be would result in getting more air into the equipment, and expensive to prevent. Okay, so you have to see if there is any leakage and how you can control that leakage and how you can recover from that leakage. Now, in terms of separators, obtain a gas phase for vapor liquid equilibrium. Now, below 1 bar, one of the reasons in the separator could be to obtain the gas phase for vapor liquid equilibrium, or we can have the temperature sensitive materials within the process. So we can operate it at less than 1 bar. Obviously, if we are operating any process below, if we decrease the pressure of any of the liquid, then the boiling point would be reduced, and that would affect the temperature sensitive material. So we have seen one example of the acrylic acid in the previous lectures, and how we can actually uh, avoid ourselves to go to reach that temperature where the material can deteriorate. Now let us see some of the process conditions and some of the more justifications. For example, if you are using some inert material in the feed to reactor, okay, so we know that we are provided with some kind of stoichiometric in the reactions, but sometimes we can use inert stream within the process, or we have to use some kind of extra reactant within the process. Now, what could be the justifications for these two things? Inert material and feed to reactor, it can act as a diluent to control the rate of reaction and to ensure that the reaction mixture is outside the explosive limits. Okay, so one of the reasons of using the inert material with the feed stream is to avoid the reaction mixture outside the explosive limits and to ensure the proper diluent. Okay, the second reason, inhibits unwanted side reactions. So if you want to inhibit any side reactions, we can have some kind of inert stream within the process. Now, what could be the penalties to the process? First one, causes reactor and downstream equipment to be larger since inner takes up space. Okay, so we are using any if we are using any additional process stream, it can be an inert stream, so it will obviously increase the size of the equipments that are installed in the process, and the downstream units also. It can be a reactor, vessel, or even the pipelines. Requires separation equipment to remove inert material. So if we are having some inert material, then obviously we have to separate that inert material to increase the purity of the product. May cause side reactions, material is no longer inert. Okay, so and sometimes it could happen that the inert materials can react with the feedstock or with the product, so that can be one of the limitation. Decreases equilibrium conversion, and the equilibrium conversion, it can be decreased because you are using an inert material or the inert stream within your reactor, then obviously it can affect the equilibrium conversion. Now, what could be the reason that you have to use the excess reactant? Increase the equilibrium conversion of the limiting reactant. Okay, so we know that why do we use the excess reactant? To increase the conversion. Inhibits unwanted side reactions. So if you want to inhibit the side reactions, we can use the excess reactant. What could be the penalties now? Requires separation equipment to remove excess reactant. Okay, so the excess reactant we have to remove from the process. Either we can recycle it back to the process, and we have to use some kind of recycle stream, and that would increase the size of those equipments and the recycle pipelines. Added feed material cost due to losses in separation and no recycle. So sometimes if there is no proper recyclation, then the feedstock, it can be wasted from the process, and it can reduce the profit margins. Product present in the feed to reactor. Now this could be one of the condition in which we can use the recycle stream from the product side, and we send it back to the reactor to convert the unconverted reactants into the products. So the products, what could be the benefits? Products cannot easily be separated from recycled feed stream. Okay, so if there are some products into the into the feed stream, then what we can do here, we can recycle the product stream back into the reactor. Some more of the feed material can go back into the reactor and increase the conversion. Recycled products retard the formation of unwanted byproducts formed from side reaction. So it is one of the use of the of using the recycled product stream. So the unwanted byproducts can be reduced from the process. Product acts as a diluent to control the rate of reaction and to ensure that the reaction mixture is outside the explosive limit for the exothermic reactions. So sometimes we recycle the product stream back into the reactor to push the reactant mixture outside the explosive limits of the process. Okay. Now, what could be the penalties on the process if we are using the product stream into the recycle? It causes reactor and downstream equipment to be larger. Obviously, the size of the reactor and the downstream equipments would be increased. It would require the larger recycle loop. So the recycle loop would be of the larger size. It can increase the size of the pipelines, decreases equilibrium conversion. So obviously, if we are using some any kind of inert stream or the product stream back into the reactor, then it will affect the equilibrium conversion. Now let us see some of the more concerns in terms of some of the equipments and what could be the justifications for those equipments. Now, if you are using some kind of compressors and the pressure conditions that we require there, it is the outlet pressure to the inlet pressure, the ratio of the outlet and inlet pressure, it is greater than 3. So usually the acceptable range for this compression ratio it is less than 3, but if it is greater than 3, then what we have to do, use multiple stages and intercoolers. So we have to use multiple stages again, and we have to cool down the gas with the intercoolers. Now what could be the penalty? High theoretical work requirement due to large temperature rise of the gas stream. So whenever there is a compression, there is a release of the heat energy, and if we do not do not cool down the gases before putting it into the next stage of the compressor, then obviously the efficiency of that process or the compressor would be highly reduced. High temperature inlet gas. So the temperature of the inlet gas is high, then we have to do the cooling of those gases before we can compress it, and it can affect the high theoretical work requirement and special construction of material requirement. So if the temperature of the gas is high, what could happen? It can increase the theoretical work, and overall the efficiency would be decreased. Now for the heat exchanger, if the delta T between the process strains it is greater than 100, then what can happen? Integrate heat pattern within the process. So we have to use the pattern heat exchanger network, or heat integration not possible or not profitable, or we can use this kind of situation with delta T between the process strain is greater than 100. Now what could be the justification that heat integration not possible? So sometimes we have to we are having such kind of process strains in the industry that we cannot integrate into the heat exchanger network. So for those processes, that is a limitation. Okay, so we can have this kind of temperature in there. Obviously, we want to reduce this delta P to maybe 10 or 20 degrees C to have the maximum heat exchange between the process streams. But we have to see these justifications in case we do not achieve that low temperature difference. Now, what could be the penalties? Large temperature driving force means we are wasting valuable high temperature energy. So if the delta P it is delta T is very high, then what does it mean? That there is a large temperature driving force. So the delta T would be very high, and we are wasting the valuable heat energy from the process. So we have to just like keep the delta T close to the inlet and the outlet conditions of the process, so we can have the maximum heat exchange between the process streams. Now process heaters, if the outlet temperature is less than the steam available. Now for the process heater, as I told you that we want to keep the delta T minimum between the process streams, so we can have the maximum heat exchange. Now in most of the industries we exchange the heat by using steam, or we are generating steam or we are heating the streams. Okay, so what we can do here, If the outlet temperature of some of the stream is less than the temperature of the steam, then the stream in the process, and what could be the solution? Use high pressure steam to heat the process stream. Now if we increase the pressure of any of the process stream, then what could happen? The boiling point of that stream can be increased, right? So when we increase the boiling point of any stream, then it can allow you to increase the heat exchange between the outlet and the inlet streams. Okay, so we can increase the pressure of any stream, so the boiling point of that stream can be increased. So then we can have better heat exchange between different process streams that are present in the process. Now what could be the justifications here? Heater may be needed during the startup. Now, whenever there is a startup, you are just after the closing of the industry, then you have to restart that process again. Then sometimes you have to supply the heat to the process stream. So in that case, we need the separate heaters that can supply the heat to the process to heat the process streams. Okay. Now, what could be the limitations? Process heaters are expensive and unnecessary if heating may be accomplished by using a available utility. So process heaters, the cost of those heaters are expensive, and usually it is required that we use the process stream or the utility streams that we have into the industry to for the heat exchange purpose within the processes. Now, if you're using some kind of valve, now what could be happen? Large delta P across the wall. So this is one of the problems. So whenever we have the valve, so we can have a drop in the pressure across that valve. So what could be the solution here? For gas streams, install a turbine to recover lost work. So instead of the valve, we can also use some kind of small turbines to recover that delta P and generate some additional electricity. But what would happen? Wasteful expenditure of energy due to throttling. So if we are having some kind of valve, so we actually waste the energy due to the throttling. So if we do not use any kind of turbines, we are actually losing the energy from the process. Okay. Now, if you want to install a small turbine on the instead of the valve to recover the pressure and to generate electricity, and what could be the reason here? Valve used for the control purposes. Now, what is the reason of using the valve here? We have to control the process, so we have to use the valve, so we cannot use the small turbine. Installation of turbine not profitable. Now, you know that the cost of that turbine, it is really very high, so we have to see the economics, and we have to see that how much energy we can generate from the turbine, the maintenance cost of that turbine, and then the annual expenditure that we need to put on the turbine, and then how much energy we can recover. So we have to do all of these calculation to look at the profit margin, whether the process is feasible while having the valve, or we can have the more better process utility using some kind of turbine. Liquid is being throttled, so sometimes we need to have the cooling of the process streams, so we can have the throttling effect using the valves. Okay, so these are some of the reasons that we have seen in terms of valve. We can use the turbine to recover the delta P, using some turbine to get some electricity, or we can use these justifications if we just want to have a valve within the process. Now, so you would also see some kinds of mixers into the industry, and what could be the effect of those mixers, and why do we use this one? Streams of greatly different temperatures can mix. So when you use mixers, so the temperature difference between the streams, they can be mixed with each other, or the streams with greater different composition they can mix. Okay, so sometimes you mix different process streams having different compositions, and both of these two things, it would result the composition of the final stream and even also the temperature of the final stream. Now what could be the solution? It bring temperature of the streams closer together using the heat integration. So whenever we want to mix two process streams, it is recommended that we bring the temperature of those streams close to each other, so the final stream, it would be having the similar temperature of the inlet streams. Then what could be the justifications of using the mixers and the mixers? Quenching of the reaction product. So sometimes we want to suddenly or quickly cool the reaction product, so we can mix different streams, providing driving force for the mass transfer, and sometimes we want to increase the mass transfer rate while mixing the product stream. So depending on your need, you can have the different justification of using the mixers within the process. Now, what could be the penalties here? Wasteful expenditure of high temperature energy. So, for example, if you are mixing the high temperature gas stream with the low temperature gas stream, then what would happen? The high temperature gas stream would be losing the energy. So, what could you do in this case? Maybe you can have some better heat exchanger network, so maximum amount of heat energy can be recovered. And once you have the similar temperature range between the different process streams, then you can mix it. The second thing causes extra separation equipment and the cost. So when you mix different process streams, obviously different components mix. Some are required, some are not required. Then you have to use the separation equipment to have the separation between the required and the unrequired products. Now let us see this example here, and we will see that how we can actually see the process reliability. It is necessary to provide a nitrogen stream at 80 degrees C and pressure of 6 bar. So this is the final, this is the inlet condition. Now let us solve this example and see that which process is more reliable and what different kinds of process alternatives we can make. It is necessary to provide a nitrogen stream at 80 degrees centigrade and a pressure of 6 bar. The source of the nitrogen is at 200 degrees centigrade and 1.2 bar. So this is the final requirement, that we need to have the nitrogen at 6 bar pressure and the temperature of 80 degrees centigrade, whereas the inlet stream of the nitrogen, it is at 1.2 bar and the temperature is 200 degrees centigrade. Determine the work and cooling duty required for the three alternatives. Now we have to make different alternatives for this process, and we will see that what is the cooling duty requirement and how much is the work required for the compression. Number one, compress in a single compression stage and cool the compressed gas. So for the first thing, that you can simply compress this gas in the single stage to this pressure, and then you cool down to this temperature. Now what could be the flow sheet? This one. So you have the gas here, you simply compress it and to 6 bar, and then you reduce the temperature to 80 bar. So this is the one alternative. Second one, cool the feed gas to 80 degrees centigrade and repeat part A. Now here you would first cool down the gas from 200 degrees centigrade to 80 degrees centigrade, and then you compress it again in the single stage, and then you cool down again to 80 degrees centigrade in this alternative B. Okay, so this is how you make the alternative B. Now the third one, repeat part B above, except use two stages of compression with the intercooler. Now what could be the third one? So the first part would be here again, and you have to just use like the interstages between the compressors. Okay, so here you would first cool down it to 80 degrees centigrade, then you compress it, again cool it, then again compress it, then again cool it. Okay, so this is the alternative number 3. Now identify any conditions of special concern that occur. So in the development of these three cases, so you have to see that if there is any condition of the special concern, if you are going beyond the temperature range of 40 to 260, or you are going beyond the pressure of 1 to 10 bar, then you have to see those conditions. Okay, so nitrogen can be treated as an ideal diatomic gas for the compression. Use a basis of this one and assume that the efficiency of each stage is 70%. Now here you are provided with the Cp of the nitrogen, then you have the Cv of the nitrogen, and then you have the gamma, the compression ratio, and then you have the value for the R and the efficiency of the compressor, each of the stage. Okay, so the equations that you can use here, there are two equations. First one, you have to calculate the amount of heat that can be recovered by the heaters. So these heaters, that how much heat can be recovered. Then the work done, the work that has to be done by the turbine. So this is the equation that you can use for that work calculation. And T out is how you can actually calculate the temperature out of the compressor. Okay, so these are the three equations that we're gonna use to study this example. So we will see all of these alternatives one by one. Now here is the summary. Now stream number one, so the system A, and then you have these streams. Okay, so if I go back to system A, so you can have stream number 1, 2 and 3. So you can have here stream number 1, 2 and 3, and the inlet stream is 200. Then you do the compression and then you do the cooling. So this one is the inlet stream, done the compression and then you do the cooling. So this is the criteria in the system B. What did you do? This is the inlet stream, then you cool down it to 80 degrees centigrade, then you increase the pressure to 6 bar and then you cool it. And in the system C, this is the inlet condition, you cool it to 80 degrees centigrade, then you compress it, okay, to 2.68 bar and then you cool it to 80 degrees centigrade, then you further increase the pressure to 6 bar, that will increase the temperature to 210, and then you again cool down it to 80 degrees centigrade at the pressure of 6 bar. Okay, so these are the three alternatives, and for these three alternatives we try to calculate the work done by the compressor. So in the system A there was only one compressor. This is only one compressor. You can use the equation to calculate the W1. In the system B there is only one compressor, but there is the inlet stream is cooled down compared to this one. Okay, so that will give you the different value for the compression. Okay, so obviously you would see a reduction in the value for the compression because the inlet temperature to the case B for the compressor it is less, so it will give you less amount, or you have to spend less amount of work on that compressor. And similarly in the case 3 you are having how many compressors, one, two compressors, so you have to calculate these two compressors. Okay, so if you look at here the overall work done by the compressor, so in the case one the work done is very high and it is reduced and then it is further reduced. So what we see from here, that if we are using some kind of compression system with the intercooling like these heaters, then we can actually reduce the work done by these compressors. So that's why in the industries you would see the intercooling stage between the compressors. Similarly, in terms of heat that can be recovered from these heaters, then what should be the value of those heaters here? Now let us see this one. In the system A, you are having just one heater, so the amount of heat that you have to recover here or going into the atmosphere is very high, 14,970. In the system B, you would be having less amount of heat in the process that is generated from the compressors. Okay, and if you are having some kind of intercooling between the compressor stages, then you have the less amount of heat that can be recovered from the process. Obviously if you are having less amount of heat generated within the process, then that process could be more efficient, because that heat if you are using that heat to heat some other process streams, then obviously you have to go for the better heat exchanger network. So our primary aim is to have the intercooling between the stages of the compressor, so the less amount of heat is generated within the process and less amount of energy recovery requirement would be required in the process. Now the third part, identify any conditions of special concern. So we have to see what are the conditions for the special concern here. Figure 6.2 gives the process flow diagrams for three alternatives and identify stream numbers and utilities. Okay, so here you can see different process streams and you are provided with the numbering here, and you know what is the temperature and the pressure conditions that you calculated here. The results of calculation part A, B and C are provided in table this one, which shows streams, conditions and utility requirements. To keep the calculation simple, the pressure drops across and between equipment have been ignored. Okay, so delta P across equipments, it has been ignored to keep the calculation simple. The part D. Alternative A requires a compressor exit temperature of 595 degrees centigrade. So in the first case, the outlet temperature from the compressor is 595 degrees centigrade. That is condition of special concern. Okay, so it is beyond 260, so it is a condition of special concern and would require the material of construction for the pipeline and for the downstream processes, that would increase the cost of the process. Note also that although the intermediate temperature of the gas stream in alternative B was 374, because this stream is to be cooled, there is no concern about the utility requirement. Obviously, in case B here, if you look at the temperature that we get here, 374, because of the intercooling between the before the compressor, then you are getting closer to the temperature range of 260 degrees centigrade. Obviously, this temperature is high, but it is not a condition of the special concern in terms of utility requirement. Now, there is one matrix here that you can see here. So this matrix basically it is taken for the process toluene hydrodealkylation process, which is represented here. Now here you have to see all of the process streams that is mentioned here, okay, and you have to see what are the conditions of the special concern if you are operating any process stream above the temperature of 260 degrees centigrade, or you are having the pressure above 10 bar, then that is the condition of special concern. Okay, so if you look at this toluene dealkylation process, so these are the names of the equipments and these are the conditions of the special concern. So you have to see each of the equipment and then you can. Now here you can see the name of all of these equipments, and here you can see the conditions of the special concern. So you can see this one R101. If you go back here, R101, it is this reactor and the outlet stream is 9. So the temperature is 654 degrees C and the pressure is 24 bar. So this is the condition of special concern. So you can put the cross here, and similarly you can see all of these equipments and you can just put the crosses here where you see that there is a condition of special concern. Okay, the same way the more equipments are here, and you would see that if there is any valve here you can put it cross here, or if there is some pressure control valve, that is a condition of special concern. So you can have this kind of table to highlight the conditions of special concern for any process. Okay, so this is all for today, and the next time we will inshallah start with the reactors and how we can actually evaluate the reactors. Okay, so thank you everyone.